This is day 1 of chapter 17, which is called Static Electricity and Electric Fields. Alright, so we're going to go ahead and get started. Start with a warm-up. What exactly creates lightning? Well, lightning is created between the clouds and the ground when you have a buildup of charges in the cloud. When you have enough charges, they could either come down from the cloud down to the ground, but they could also go from the ground up to the cloud, between clouds, and sometimes they can even shoot up into the atmosphere. So that's what creates lightning, a buildup of charges. Alright, our lesson objective for today is students will find out about charges and how they exert attractive and repulsive forces. Alright, so first part is, what is an electric charge? The study of electric charges that can be collected in one place is called electrostatics. That's what we're going to go ahead and talk about. Now, right here you have a young man who's touching probably a Van de Graaff machine. He's building up a lot of charges, and notice his hair stands up. Alright, why does his hair stand up? The reason for that is that as the electrons move into his hair strands, they repel each other. So they want to be as far away from each other as possible, so you get that round pattern. A substance that allows charges to move through it easily is referred to as a conductor. In a plug, the metal parts, those are conductors. Charges can easily move through them. What about if charges cannot go through them? That's called an insulator. For example, all of this black rubber part around the wire, those are insulators. Charges cannot go through the insulated parts. This is a picture of an electroscope. An electroscope can be used to detect a charge. So it's a very simple device. It's got a metal ball on top, and at the bottom it's got two leaves, usually made up of some metal. And when there is no charge, well, the leaves are close to each other. But when there's a charge nearby, the charge will go into the electroscope. So it's their little electrons, and they'll build up. And since they repel each other, what you will see is that repulsion manifested by the movement of the leaves go further out. Since the electrons repel each other, they'll move further out. So the electroscope can detect, yeah, there is a charge present here. Alright, so here's the explanation. It says the leaves of the electroscope can be charged by conduction. Conduction is the actual transfer when something is actually touched. Alright, so let's go ahead and take a look at the different types of charging. The first one is the process of charging an object without touching it is called charging by induction. So in this example, we're going to go ahead and have two metal spheres. And we're going to go ahead and put a balloon next to it. Now this balloon, if you notice, got a negative charge. So what does that do to the charges? The positive charge will move towards it, and the negative charge will move away. Opposites attract, so that's why the positive are going towards the negative balloon, and negatives repel. Once that happens, we can then go ahead and separate the two metal spheres, and those charges will stay. All the positive charges will stay here, and the negative charges will be on the other one. So you have positively charged the first sphere and negatively charged the second sphere. Alright, so that is charging by induction. You can also charge using grounding. Alright, so how does that work? In this one, we're going to go ahead and have our metal sphere again and expose it to a balloon. This time the balloon has a positive charge. What does that do? Well, the electrons are going to move towards it because opposites attract. So the negative electrons move towards the balloon, the positive charge will go away from it. Then you can go ahead and make a contact with the positive charge. That will allow the positives to exit through you. And once you let go of it and the balloon moves away, you're left behind with only negatives. Alright, so that is charging through grounding. Now we're going to go ahead and move on to Coulomb's law. And Coulomb's law says in 1785, Charles Coulomb measured the force between two charged objects, and he used this little device right here. Let's look a little bit about how it works. So we know that charges that are of the same, they are going to repel. So you had a device that looked like so. In it is a wire holding two spheres on each side, and he went ahead and charged them with electrons. So there's electrons all around these. Then he exposed it to another sphere that also had electrons. He kept track of how much charge he was putting into it. So what happened to this section? Well, these repel, right? So they moved away, and so it twisted. how much force does it take to twist this little bar? He went ahead and measured that. So he figured the force needed to twist this section of the device was equal to the force exerted by the repulsion of the electrons. So he did some calculations and he was able to figure out that force. He made the following conclusions. He said that the force exerted by a magnetic field depends on the distance. So the force is 1/2 or the inverse of the radius of the distance squared. So the further apart they are, the less force they exert on each other. And also pointed out that the force is also equivalent to the charge. So if he added more charges, so I'm going to put more electrons, then this section of the device will move even further, will twist even more. Alright, so there's a relationship between the charges and the force and the distance and the force. So that's inversely proportional because the further they get from each other, the bigger the distance, the smaller the force. But on the other side, the charge is directly proportional. The higher the charge, the higher the force exerted on this part of the apparatus. Then he combined them to put together this formula right here, which we'll be using. In this formula it says Fe, that's the force due to the electric charge, is equal to the constant, Coulomb's constant. You can figure that out. The value is 9.0 times 10 to the 9 newtons times meter squared divided by Coulomb squared. And then you multiply that times the charge of A and B. So we have our first section's A, second section's B, and divided by the distance, which is squared. So R is the radius measured in meters. Alright, so that is a formula very similar to another formula we've used before. This is the force due to gravity, versus G is the gravitational constant, which is value is 6.7 times 10 to the negative 11. MA and MB will be the mass of object A and object B, and R is the distance between them in meters. Alright, useful information, and this table we'll refer to from time to time as we're solving problems. Let's see, charge and mass of atomic particles. So here are the particles, electrons, protons, and neutrons. Their charges are negative 1.6 times 10 to the negative 19 coulombs for the electron, positive 1.6 times 10 to the negative 19 coulombs for the proton, and for the neutrons got no charge, it's neutral. Their masses, here they are. The electron is the smaller of the three, 9.1 times 10 to the negative 31 kilograms. For the protons, 1.67 times 10 to the negative 27. And the neutron, which is slightly heavier than the proton, it is 1.67 times 10 to the negative 27 kilograms. Alright, so those values will be referred to from time to time. They're going to ask you guys questions such as, what's the force from one proton to the other proton, or between one proton and another electron? And the values for these, we'll get them from this table. Alright, so up next for us is sample problem A out of page 565 of your textbook. It says, an electron and a proton of a hydrogen atom are separated on average by a distance of 5.3 times 10 to the negative 11 meters. Find the magnitude of the electric force and the gravitational force that each particle exerts on the other. So there's two forces acting on it. You have the proton and you have the electron. They're opposite charge. The proton is positive, the electron is negative. They attract each other. On top of that, there's another force of attraction. It is the fact that both the proton and the electron have a mass, and any object with mass, we're going to go ahead and have gravitational force towards each other. So they asked us measure both, the force of attraction because they have a charge, and the force of attraction because they have mass. So electric force and gravitational force, that's what we'll be looking at. Alright, so let's go ahead and take a look back at the formulas. For the first one, for E, for electric field, let's see, it is Fe equals the constant, Coulomb's constant, multiplied times the charge of A times the charge of B over the radius squared. So let's see, it is a proton and an electron. So we're going to use this table as I mentioned. Here are their charges. We're going to plug them in here for the proton and electron. The distance was given to us in the problem. So let's just start solving this problem. Fe equals the constant, 9 times 10 to the 9 newtons times meter squared over Coulomb squared, multiplied times the charge of the first one, the electron, 1 times 1.6 times 10 to the negative 19 coulombs multiplied times 1.6 times 10 to negative 19 coulombs. For this one, we're going to put negative. That's our electron. This is positive for the proton, though the charges really do not get too concerned over. We know that one's positive, one negative, they're going to attract towards each other. Alright, and all of this will be divided by the radius, and the radius was given to us in the problem. The average distance between them is 5.3 times 10 to the negative 11. 5.3 times 10 to the negative 11 meters. And do not forget that that is squared. Alright. Now some of my students like to put all of this at once into the calculator. I prefer to go step by step. I'm going to multiply all the numerators together, then take care of the denominator, and then finally divide. So I have 9 times 10 to the 9 times 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19. That gives me 2.30 times 10 to the negative 28 divided by 5.3 times 10 to the negative 11 squared gives me 2.81 times 10 to the negative 21. And then I just divide both of these numbers, and that will give me my answer. That is 8.19 times 10 to the negative 8 newtons. That is my force. That is the force between the proton and the electron due to their opposite charges, so their electrical force. In the next part of the problem, they said, alright, we want the electrical force, which you got it. Can we also get the gravitational force? No problem. Alright, for that one, we're going to use this formula. Force of gravity is equal to G, the gravitational constant, times the mass of one object, multiplied times the mass of the other object, and the distance between them squared. Alright, so I'm going to solve it down here. Value for G. Let's look that up. G, 6.7 times 10 to the negative 11. And that's in newtons times meters squared over kilograms squared. Next is going to come the mass. The mass of a proton. We're going to put that one first, or let's put the mass of the electron first. I'm going to round it up slightly. 9.11 times 10 to the negative 31 kilograms. Multiply times the mass of the proton. 1.67 times 10 to the negative 27 kilograms. And all are divided, same distance. 5.3 times 10 to the negative 11 meters squared. Alright, so I do have the denominator. It's going to be the same for both. So it is 2.81 times 10 to the negative 21. Let's get the numerator. So we're going to multiply the G times the mass of one times the mass of the other. And that's going to give us our numerator, 6.7 times 10 to the negative 11. Multiplied times 9.11 times 10 to the negative 31. Times 6.67 times 10 to the negative 27 gives us a grand total of 1.02 times 10 to the negative 67. You can divide both of these values. Alright, and that gives us 3.64 times 10 to the negative 47 newtons of force between them. Alright, now we got the force due to electricity, the force due to gravity. I want you guys to notice something. That is 0.0, well, times 10 to the negative 8. This was times 10 to the negative 47. This value is very small. 47. Alright, imagine that, all those zeros before we get to 3, 4. This value is so small that it's almost insignificant. So when we solve this type of problems, we only really look at the electric force between them. And students sometimes ask, but isn't there force of attraction due to gravity between them? And they said, yes, there is, but it's so small that we don't really take it into account. Alright, so that's the first and last term in this chapter that we'll solve for force due to gravity for these. And you can see why. It is Very, very tiny. All right, so that takes care of sample problem A out of page 565. All right, our next problem is practice problem number 1 out of page 566. A balloon is rubbed against denim and it gains a charge of -8, see the symbols microcoulombs. What is the electric force between the balloon and the denim when the two are separated by a distance of 5 centimeters? Alright, so first of all, notice that they only give you guys one charge. So picture that. They get the balloon, they rub it against the pants. So what happens to the electrons? Well, they're going to jump to the balloon. So it develops that charge. What do I charge? -8 microcoulombs. But we need two charges to answer this problem. If the balloon got 8 microcoulombs worth of electrons on itself, then how many electrons or what charge did the pants lose? Because it has to lose some charges. The answer is the pants will have the same charge but positive. Positive 8 microcoulombs. So the pants becomes positive because it sent electrons over to the balloon. So the charge of the pants is this, the charge of the balloon is that. So it's the same charge. Now you've also noticed that it's in microcoulombs. You cannot use that. It's got to just be in coulombs. So how do we change microcoulombs to coulombs? That'll be our first step. So let's start with our charge. So Q for the balloon, I'm going to put a B right there. It's going to be -8 microcoulombs. But we need it in coulombs. So how many microcoulombs is there in 1 coulomb? The answer is 1 million. So microcoulombs cancel out, so there's going to be 8 multiplied times 1 divided by 1 million. And our answer comes out to be 8 times 10 to the -6 coulombs. Alright, so that's our first part. Changing it from microcoulombs, you divide it by 1 million. So we end up with 8 times 10 to the -6. See, we divided by a number that had 6 zeros in it, so that's why it's a -6. Alright, so now we have the charges in coulombs. The next one is, let's see, 5 centimeters. No, we can't use that distance in centimeters. It's got to be in meters. Alright, so our distance, or our radius, is going to be 5 centimeters. In every 1 meter, there's 100 centimeters. Alright, so we have 5 times 1 divided by 100. It gives us 0.05 meters. Alright, so we got our charges in the proper unit. We got our radius, our distance between them. Alright, and let's figure out the force. The electric force is going to be K, the value for the Coulomb's constant, which is 9 times 10 to the 9 newtons times meter over squared over Coulomb squared. So that is a constant. We always use that number for electric force. So that's our constant. Next comes the charges. Remember, the charges are going to be 0.8 times 10 to the -6 coulombs multiplied times +8 times 10 to the -6 coulombs divided by the distance between them, which is 0.05 meters. And don't forget that that value is squared. Alright, so let's plug them into the calculator, see what we get. I'm going to multiply all the numbers on the top, so it's going to be, let's see, 0.8 times 10 to the -6. I'm going to square it because it's the same number twice. Multiply times 9 times 10 to the times 10 to the +9. Goes ahead and gives me 0.576. That's our numerator. Multiply those three numbers. 0.05 squared gives me 2.5 times 10 to the -3. And then just divide both of those values. And I get my answer. I'm going to round it off slightly. 230 newtons. That will be the force of attraction between them. 230 newtons. Alright, that is practice problem number 1 out of page 566. Up next is practice problem 2 out of page 566. In this one they ask, you have two identical conducting spheres. So here's one, there's the other. They are 0.3 meters apart. They're given a charge of 12 times 10 to the -9 coulombs for the first, and for the second, negative 18 times 10 to the negative 9 coulombs. Then they ask you two questions. The first one, find the electric force exerted on one sphere by the other. So we're going to go ahead and use this formula right here. So Fe equals the constant times the charge of one times the charge of the other divided by the distance between them squared. Alright, so let's go ahead and get to work on them. Fe is equal to the constant 9 times 10 to the 9 newtons times meter squared over coulomb squared. That's the constant. Then their charges. 12 times 10 to the negative 9 coulombs multiplied times negative 18 times 10 to the negative 9 coulombs. All of it divided by the distance between them, which is 0.3 meters squared. Alright, so now we have all of our values in. Let's plug them into our calculator. And we're going to have 9 times 10 to the 9 times 12 times 10 to the negative 9 times 18 times 10 to the negative 9. That's going to go ahead and give us 1.94 times 10 to the negative 6 for our numerator. For our denominator, 0.3 squared, it's going to give us 0.09. And then I just divide it to get our answer. 1.94 times 10 to the negative 6 divided by 0.09 gives us 2.15 times 10 to the negative 5 newtons. So there's the answer for part A of this problem. Now in part B they ask a similar question, but they say the spheres are connected by a conducting wire. After equilibrium has occurred, find the electric force between the two spheres. Alright, so what happens to a sphere once we connect them to a wire? Well, you see the positive and negatives, they're going to go in the wire, and positive and negatives, once they meet, they cancel each other out. But notice that the negative is more than the positive, so they're going to have some negative left over. How many? Well, let's check it out. So it's going to be 12 times 10 to the negative 9. They're positive minus 18 times 10 to the negative 9. So we subtract, the answer is 6 times 10 to the negative 9. So that is the charge that is left over. Okay, so 12 times 10 to the negative 9 charges got canceled out. So that's what's left over. By the way, they are negative charges. Alright, now, so how are these charges distributed? Well, they're no longer these. It is only 6 times 10 to the negative 9. But are they here or are they there? The answer is they are split evenly between them because they are the same size. So in this side we're going to have negative 3 times 10 to the negative 9. On the other side, negative 3 times 10 to the negative 9 coulombs. Alright, so that will be our new charges. In part B, now they want to know the force between them. So very much the same setup for part B, except the charges are changing. So it is 9 times 10 to the 9 newtons times meter squared over coulomb squared. And now the charges, negative 3 times 10 to the negative 9 coulombs. Negative 3 times 10 to the negative 9 coulombs as well. All of it divided by the same distance, 0.30 meters squared. Alright, so now we plug that into the calculator to get the answer. This is going to be 9 times 10 to the 9 times 3 times 10 to the negative 9 squared, because there's two of the same, divided by 0.3 squared equals, the answer is 9 times 10 to the negative 7 newtons. That is for part B. Alright, now, I do want to address the positives and negatives. Notice how in part A, you have one negative, one positive. And what happens to opposite charges? Well, they attract. So this one should be attract. But here we have two negatives in part B. So that's a force, but the force, because they're both negatives, they're going to be repelling each other. Alright, so that's how you use the charges. So you don't really see them on the answers. In case you're wondering, well, what happened to that negative? I don't see it in the answer. No, that's just to figure out, are they going towards each other or away from each other? If they both match, they repel. But if one's positive, one's negative, they attract. That is practice problem number 2 out of page 566. Up next is practice problem number 3 out of page 566. In this problem they tell you you have two electrostatic point charges of 60 microcoulombs and 50 microcoulombs, and they exert a repulsive force on each other of 175 newtons. What is the distance between these two charges? Alright, so solving for this, we're going to go ahead and look for R. So let's isolate the R. I'm going to begin by multiplying by R squared on both sides. So that will make that go away. Now I want to isolate the R further by getting rid of the force. I'll cancel it out. So what's left on the left side, it is R squared is equal to the constant times the charges over the force. Now I want the R, not R squared, so I'm going to square root this side and square root the other. And when I square root the square, it just goes away. So there's our formula. Next, these are in microcoulombs. I need them in coulombs. So it is 60 microcoulombs. I multiply it times, for every 1 coulomb, there's 1 million microcoulombs. So the answer it is 6 times 10 to the negative 5 coulombs. Over here, we're going to do the same to the 50. So our answer it is 5 times 10 to the negative 5 coulombs. Great. So let's start plugging in values in here. So we have R is equal to the constant 9 times 10 to the 9 newtons times meters squared over coulomb squared. Multiply times the two charges, which we have right here. 6 times 10 to the negative 5 coulombs times 5 times 10 to the negative 5 coulombs. All of it divided by the force, which is 175 newtons. Okay, and the whole value square rooted. I'm going to start by multiplying the numbers on the top, then dividing by the number on the bottom. And let's see, we got 9 times 10 to the 9 times 5 times 10 to the negative 5 times 5 times 10 to the negative 5 equals 27 divided by 175 gives me the following. 0.154. After that, I square root to solve for the answer. 0.39 meters. That is how far apart these 2 point charges are. So there's practice problem number 3 out of page 566. Alright, last part of the lesson, of course, is to practice a bit. So homework number 37, page 581. Do problems number 15 and 16.